American University in Bulgaria.
Okay, Metodi, the floor is yours.
Thank you. Today, today's two topics actually, because we're gonna cover two lectures today as last time. Would build on what we did last week, just to remind what we kind of discussed. We kind of defined what risk is and what a risk management system should look like, and what kind of questions usually are asked from one such system. And we also covered what data the system utilizes. Now, today we're going to see how this data is managed, what analyses are run on the data, what kind of outcomes and answers we get from the data. And we're going to see a little bit about the actual risk system these lecture notes are based on, in the cognitive system, and discuss a little bit how the whole thing works in a complete manner. So, but for the first hour or so, we're going to discuss a little bit about statistics. We're going to talk a little bit about statistics and what analyses are performed on financial data. And the general agenda for this is basically to discuss a little bit about probability theory, just to set up some notions that we're going to need. We're going to discuss univariate and multivariate models, and we're going to talk a little bit about factor models. So, in the second lecture, we'll see how all of these come together. Now, we'll be concerned with what a probability model is and how it is used for modeling financial data. Now, a probability model can be something very simple. One variable follows a given probability distribution and that's it. Or it can be something a little bit more complex. We can have one model for the expected value of the variable, which, for example, can be ARMA, if this rings a bell. We can have a separate model for the volatility of the variable, which we'll see a little bit later on. And both of these models can be a set of equations with certain parameters and certain random drivers underneath. So it can actually be something quite complex. And the way we're going to set up the model is to write it down, basically. And we need to know all the parameters of the model, all the parameters of the distribution, and so on and so forth. And the reason we do this is that once we get the model, we can actually think about how we can fit it on the available data. And this is the actual data mining process here. We'll be taking the data, seeing if it conforms to the model, and making some predictions afterwards from the model, or doing some tests to see where this model leads us. Now, even last time we discussed a little bit about random variables, but I wanted to make sure that we have a good working definition of what a random variable is. Now, the basic thing is that there is some randomness, something unknown about the variable. A coin flip is a good example, a dice roll, or what tomorrow's price of IBM would be. That's a random variable for us. In there is kind of two separate notions. So one is that the process is truly random. Think quantum mechanics, where it's something that really is randomized and there's nothing to it. Or there are so many things going into what the value would be that for all intents and purposes we cannot solve the equations or all the machinery that is needed to find what the value is, and we can treat that as random. Of course, the point of complex models is, of course, to strip away all that we can actually say about a process. Say, we're thinking about throwing a dice. We can model what the speed of the hand is, in some sense, and we can take that out of the randomness. We model that in a non-stochastic way. We can discuss what the surface we roll is and take that out of the equation in some sense. And what this would leave us is something which is a little bit easier to handle, but there is equations on top of that. And that would be basically the complex model. An outcome of a random variable is basically what the potential result is. So you can think of an outcome for dice being 1 to 6. 1, 2, 3, 4, 5, 6. That would be the outcome. A sample space is all the possible outcomes of rolling one dice, for example. There are 6 elements in that space, 1 to 6. Building up to this is the event. Event is a very interesting thing because we'll need to speak about events rather than outcomes. An event is a combination of outcomes, basically a subset of the probability space. You can think of event as being 1 to a single roll of the dice, but it could be is either odd or even. You actually have multiple outcomes in the event. So the event is defined as being odd roll of the dice. And the reason that we actually want to see more in that is that for financial data, an outcome is kind of very difficult to define for continuous variables, I think. Actually, yeah, that's the next slide. Because we would like to assume that we are dealing with continuous variables. And a continuous variables is basically a variable for which the outcome is an interval in some sense. So it's between -1 and 1. And there are infinite number of outcomes in that interval. So you actually want to look at an event which would be defined as a given subset of that interval, no matter how complex that interval or subset could be. So we will not go and discuss too much about discrete random variables. Dice are always a discrete random variable. Rather, we will be concerned more with continuous. Basically assuming that prices, interest rates, all the stuff we saw last time, they are defined on an interval. So not so much the price, but rather the return of a random variable will be from -infinity to +infinity, logarithmic return, of course. So once we have the variable, we need a way to actually work with it. So the random variable is just something that maps to the probability space. But in order to mathematically work with it, we need a function. And the function usually is the probability density function, if it's absolutely continuous random variable, or the cumulative distribution function. That's in the book, of course, which it's an interesting way to define it, because basically we have some properties of the CDF. It's non-negative, non-decreasing and whatnot, but rather here is the main part and the reason why we need events. This is an event, this thing here, x less than or equal than t. So we have an interval, let's say started from -infinity and going up to infinity. And this interval, we split it at t. And we look at this event here. So it's a subset of the whole probability space. And what we say is that, okay, we want to know what the probability of this event is. What are the odds, or what is from 1,000 experiments, how often we will see this event becoming true? And the answer is given us by the cumulative density function. The link between the PDF and the CDF is basically an integral. So this allows us to actually do a lot of stuff, to be honest. Now, rather nice looking PDF. So this is a general graph of a random, or rather not random, but one probability density function. So if we have 0, for example, here, it doesn't really matter what the numbers are, but it's always non-negative. It's always up. It cannot be negative, and this area here under the curve basically gives us the probability of the random variable being from A to B. And that's everything we have from this equation and from this link. Now, if we know the CDF or the PDF, we know everything there is to know about the random variable, but it's a little bit different to imagine the function and all the values that it can attain and areas under the curve and whatnot. That's why we usually describe the variables with certain measures. And it's much more intuitive for people to look at one number and say, okay, I understand that, rather than showing them a function and saying this is the PDF of the random variable. And they're usually, these 5 measures are the most common ones to be used, and we're gonna go through them one at a time just to discuss them and show them how they are used. So the first one is location. It basically gives the center in some sense of the distribution. So you can think of location. It's usually defined in terms of the expected value of the random variable, its mode, which is the most probable value. It's a little bit difficult to speak about it in continuous variables, or the median, where basically the 50% quantile is. But it gives us a location somewhere around here at the center. So if this is the maximum here, this value would be the mode. The median would be maybe somewhere here, and the mean can be somewhere around here. They're all measures of location, of centrality of the random variable. Now, the funny thing is, if we're looking at symmetric random variables, say the normal distribution or anything that has equal probability to be on the left or on the right of its location center, these 3 would actually be one and the same. So this is location. Dispersion is a measure of how spread out the variables are. So what you would like to know is how large this thing here is. So If this is small, there is less variability in the outcomes of the random variable. If it's large, you're looking at much more spread out values somewhere in the interval. Two measures I've written down. We already saw them in the first lecture, actually, the standard deviation and the mean absolute deviation. They are kind of common usage for this. Asymmetry. Asymmetry is a way to judge which of which of the tails is more probable. If they're equal, there is no asymmetry. So we're speaking about symmetric random variables. But let's say you take take this thing here and this thing here, and you make them equal. 2.5%, 2.5%. So you have equal probability to be here and here. And then you compare these values, A and B. Of course, you take into consideration the location. And if they're equal after centering, you're more likely to look at the symmetric variable. If they are not equal, of course, you have asymmetry, and then the question becomes which is a heavier tail, which is more further away from the center, A or B. And linked with the tails, we have concentration in tails, which is basically fat tailness or peakness, is another way to say it, in the center here. So this bell curve kind of looks like a bell curve, but we can have something a little bit different. We can have something like this. And this goes a little bit more. So you're much more peak. You have a larger peak here in the center, and the probability of larger events compared to, say, somewhere around here is much more pronounced than the first one. So this basically is captured with the kurtosis, if it exists. Of course, it might not even exist, in which case you actually have even fatter tails than usual. I didn't mention this, but for asymmetry, we're looking at the skewness, which kind of makes the first four measures comparable to the first four centered and scaled moments of the random variable. So location will have the first moment, dispersion will be looking at the second moment, centered, and for the third we'll have the centered and scaled. Third moment will be the skewness, and kurtosis is the fourth moment, centered and scaled. And which brings us to the last one. And quantiles are interesting in that I already use them in a sense. This is the 2.5 quantile, and this is the 97.5 quantile. This is 2.5 quantile. So basically, you're looking at what are the outcomes that would have a certain probability. So you actually write something like this. The random variable, Z is the unknown number that we seek, and we say that we need this to be 25%. So whatever Z turns out to be, that's a 25% quantile. So you're solving in this in inverse. And of course, the way to do this is to take the inverse CDF, and this would give us Z. Sorry, I tend to write fairly ugly when it gets down to the bottom of the board. So that's a quantile, and if you remember from last time, we actually saw this before. and this was the value at risk number for random variables. And we spoke about why a good risk measure would actually look at more the losses than the gains. Same thing here. We'll be actually more interesting in 0.1 quantile, which would be var at 99%, 0.05, which would be var at 95%, and so on. But of course, people look at all these measures. Other measures are also interesting. You can come up with all kinds of measures as long as they are intuitive to you and they kind of make sense. For example, one can look at B over A, the quantiles in terms of skewness. You can also do something more. You can actually calculate the expected tail loss and return. We saw that last time. We take the quantiles. We estimate what the expected value here and here would be, and then divide those two. And it's quite an interesting measure, and we can actually use it for portfolio optimization later on. It has a name, Rachev ratio. So yeah, all kinds of interesting stuff. Any questions here? If I'm going too slow or too fast, please say something. I have a set schedule in my mind, but I'm kind of guessing if it's quick or slow. The usual and the nice example for random variables is the Gaussian distribution, also known as the normal distribution. It's quite old in terms of usage. Laplace, I think, was one of the first to use it, but I may remember that wrong. In any case, it was the first one to be used for financial data. And the reason for that is it's kind of easy to work with. It has some nice properties, and there is a lot of statistical tests, a lot of work people have done in statistics based on the normal distribution, and it was easy to use those tests and that work and apply to financial data, of course. There was not much effort involved in utilizing it. Now, we use it for log returns for stock, or we can use it for first difference for interest rates and so on. Almost any financial data can be modeled with a Gaussian. Can be does not mean it's good to model it with the Gaussian distribution. And the reason for that is the Gaussian is symmetric distribution, so we're not looking at different tails, and it actually has its kurtosis is normal, and the reason people call it normal is because that's the usual thing. It's very indifferent to what is happening. And when you open up a textbook on statistics, you are actually going to see not so much kurtosis, but excess kurtosis. And it's in excess of the normal distribution. So you're actually comparing everything with the normal distribution. Every distribution you see is going to have an excess kurtosis, which is in comparison to the normal. So lighter tails, there's not much probability here, and the values A and B are kind of smallish. The actual formula I've written in here for just having it written down. It's quite well-known formula, but we have an exponent of squared difference between the values and the center. And this square difference is scaled with the standard deviation, the 2 times the variance basically. And this thing here basically makes it so that we have integral of 1. There's a lot of things that can be said about this function. We're not gonna go too much in there. The expected value is mu, which is here, as I said. The standard deviation is sigma. Skewnesses and excess kurtosis are 0. We don't have the CDF in closed form. That's why when you solve problems with the normal distribution, you usually have tables which have tabulated the standard normal. And standard normal is basically with mu 0 and sigma 1. But in practice, you usually compute it on the go. There are efficient algorithms for solving the integral, for inversing the CDF, so there's not much there. And part of the reason why normal is nice to work for financial data is this: the sum of two normals is a normal distribution again. And this has actually 2 components to the fact. If you take 2 stocks and sum them up in a portfolio, the portfolio is actually going to be normal as well. So you can kind of model the whole portfolio as a distribution, as a random variable itself, even though you know what's in there. But another reason is take consecutive days. One day's return is normal, next day return is again normal. What's the return over the 2 days? It's normal again. So we have this both temporal thing going on and in a portfolio as well. So it's kind of nice to work with. And the other thing that I personally find fascinating about it is the central limit theorem. Hopefully, I'm not giving too much details here. It's a really nice theory, and you should definitely take a look at it. But it says the following: if you take something small and you replicate it many times over, and you sum it up and do some scaling and basically standardizing it, removing the expected value and dividing by the standard deviation, this sum will tend to a Gaussian distribution when the number of summands tend to infinity, as they become more and more. And why this has bearing for the financial time series? Imagine individual trades. We discussed this last time a little bit. You have trades and the price go up and down a little bit, it moves around. But the log change in price from day to day, it's a sum of small changes from each individual trade. And when you look at it in this way, you have a sum of random variables. The individual changes from trade to trade may not be normal, but their sum will tend to normal, to tend to Gaussian. So that's an applicability of the central limit theorem. And of course there are some caveats here. You have to assume that these small changes in the price from trade to trade have finite variance. So the variance needs to exist in order for this to become normal, Gaussian in the limit. But since people initially believed that these price changes cannot be that large, so it has a finite variance, it's kind of okay to use the Gaussian. Well, that's, well, not wrong assumption, but certainly questionable. And when people started looking at this, even in the 1960s, believe it or not, Mandelbrot was one of the first to acknowledge the fact these changes may not have finite variance. And if the summands do not have finite variance, then their infinite sum cannot be Gaussian, because it's not working in this way. But it turns out that there is a way to rectify this situation. And there was already a theory in place, and the theory is generalized central limit theorem. And it basically says the same thing as the central limit theorem, but removes the requirement that the summand has finite variance. Of course, what you get at the end cannot be Gaussian. Rather, it turned out that a whole class of distribution exists called the stable distribution, the alpha stable. Rather, a large naming convention exists, but the limits of the infinite sums are stable distributions. So there exists a distribution that will take care of summands even without finite variance. And these turned out to be quite nice for all kinds of financial data. Some things about the stable distribution. The Gaussian is a member of the class. So if you have summands, and no matter if they have finite variance or not, they go to a stable distribution, and you have that if they have finite variance, they go to a Gaussian. Of course, Gaussian will be a member of the stable family. And you can actually show this in different ways. And they actually have 4 parameters. One, this I didn't read them down, but usually we have alpha for fat tailness, and it goes from 1 to 2, like this. It controls how fat tails are. So alpha equal to 2, we actually have Gaussian tails, and the distribution is Gaussian, but anything less than 2, we have fatter tails than Gaussian. We have skewness. People usually use beta for the skewness, and it controls the asymmetry. And beta of 0 basically means that there is no asymmetry. And beta of 1, we have distributions like this, and beta of minus 1, we have distributions like this. Scale and location, same thing here. Basically where the center is and how spread out the values are. And it turns out that it's quite nicely linked with the characteristics of random variables. The first 4 we saw, the moment ones. They're actually the unfortunate thing is that we don't have moments larger than alpha, which basically means for any stable distribution we don't even have variance. So the variance is infinite, which precludes the usage of a lot of statistical tests, unfortunately. But these 4 parameters are kind of linked with the usual characteristics. And one more quite interesting thing is that the sum of 2 stables is again stable. And actually, this is the way people usually define the class. This is a class of random variables. If you took 2 identical, independent and identically distributed copies of it and sum them up, you'll get the same random variable, basically. Of course, you have to do some scaling and moving around to get the location and the scale correct, but it's not really that interesting. So the stable distribution basically provides a much better fit for the financial time series. And when Cognitive was first launched in 2001, if I remember well, I wasn't in the firm back then, but the main thing that separated us from our competitors was the usage of the stable distribution. Our chief scientist has done a lot of work in these distributions, a lot of academic testing and books and articles and whatnot, and we use that knowledge to kind of create the whole machinery behind that. And we've been expanding the models and what we're using since. And actually, what we have here, some other facts about the stable distributions. I already mentioned that we don't have a second moment. We actually cannot then talk about variance, skewness, and kurtosis, but of course, asymmetry and fat tailness are still defined. There's no problem with using those, where just skewness and kurtosis and variance are out of the question. Unfortunately, the PDF is not known in closed form, so you cannot really write it down as such. The same goes for the CDF. What we usually work with is the characteristic function, but I don't really want to go there in terms of math. That's it. Simulations, quite easily produced. There are formulas, straight simulating. And estimation of parameters, we're going to talk a little bit about that in the second lecture, but there are also all kinds of methods. Some based on maximum likelihood, numerical estimation of parameters. There are quantile based methods, there are regression based methods, and so on and so forth. Now, while the stable produces a better fit, much better fit than the Gaussian, the lack of variance is somewhat troubling, because we're not seeing too large movements on the market. So a given stock would not change by 10,000% on a given date, which the stable distribution sometimes predicts could happen in a million simulation. One can be something like this. So because we're not seeing that, some work needs to be done, not to actually use the actual stable, but something a little bit more. This can be done numerically, but a little bit better approach is actually to do it theoretically. And for this reason, tempered stable distribution, a whole class actually, was developed not in particular by us, but we did have some input here. And the idea is to actually, if we look at this PDF here, so it's something like this, but the easy solution would be to say, okay, I'm gonna cut it here. Anything afterwards, I'm not gonna use it. We can put even something which goes to zero quite fast, something like this. And this is an easy approach to take, and it would work in a sense, as far as financial engineering would imply. But an even better approach is to multiply the whole distribution starting from here and with a different one over there with a function that would go to zero quite fast. So now for the stable distribution, we actually know how fast this function tends to zero. It goes something like this. It's all small, and it's a polynomial. Yeah, it's x to the power of minus alpha speed. The normal has e to the power of minus x2, because that's the PDF, and this is how fast it goes. So the idea was to take the PDF of the stable and multiply it with something that would go faster than the usual speed to zero. And the tempering function, they usually look like something like this, times some parameter. And this would be the tempering function, and we will apply it from here all the way to minus infinity, and from here all the way to plus infinity. And this would ensure that we actually have moments. And we have every moment, just like the Gaussian, because it's quite so fast moving to zero. And it turns out that this leads to quite interesting and somewhat not better, because it's a little bit different to quantify which one is better, but certainly interesting results. It's a little bit more appealing, which again is not quantifiable as such. But it's better to say to a practitioner, okay, the model actually has variance. We're not predicting that tomorrow's return of your portfolio would be plus infinity or minus infinity, and it actually works out nicely for other problems as well. For example, option pricing. We saw last time how to price an option. I just gave you a formula which was based on the Gaussian distribution. The process for the stock swap returns were Gaussian, but we already know that it's not really Gaussian. So the implied volatility has to be put on top in order to rectify the difference between theoretical and market price of options. But another possibility is that we actually take out the Gaussian and put something there. We cannot really put stable in there. The mathematics doesn't really work that well. It's possible, but we're not getting the best possible answers. The temper stable, though, shows much more promise in being utilized for option pricing as such. So it's quite appealing for financial instruments. And I believe we're actually the only vendor in the financial risk management space that offers temper stable distribution as such. Now, I have here, just a second please. I want to discuss with you a concept of subordination and how we apply it to finance and how we use it and so on and so forth. The idea is the following. Take this here. If you have the graph of a price and we have time here and here is dollars. You're measuring the price, let's say daily. So the unit here would be day, 1 day. You have one price today, another price tomorrow, another price the day after. So the changes in time is a single unit 1 day. But here's an idea. Say today was a slow news day. Russia didn't do anything, North Korea didn't do anything, no new earnings were posted, the Fed was quiet, everything is normal. You don't have that much price changes in the function. So everything is kind of normal and quiet, and you're not moving anything too much. But what happens if, Russia did something, North Korea fired another missile to test it, the companies issued earnings. It's a fast news day. There are a lot of news on the market and practitioners are reacting to that. You have much more changes to the price. And we can actually use this idea. And the idea is a subordination. You have one process that goes with a single unit of market time. And this is a normal Gaussian process. But then you simulate another process, a subordinator process, which basically gives you is it a slow or a fast news day? So how quickly market time will change from day to day. So for a normal day it could be 1. For a fast day it could be 2. For a really slow day it could be 1.5. And what this does is that, let's say, a single unit of normal time would be something like this. Well, not much change. But then you cram this thing into half a day, and then you have something like this for the second half. So this would be for half a day, 1.5 days. And then you have another one just the same for the next half day. So half day of normal time, but in business days you actually have 2. So you're seeing a larger movement in the price. And it turns out that it's a very powerful idea and can be used quite interesting for financial time series. And you can actually explain, just as I did today, to practitioners, and they get it. There's no fancy map. You just talk about fast moving news and slow moving news. And it's quite powerful. And the interesting thing is the stable has a representation as a subordinated process. The subordinator is, of course, something which is a little bit more complex and difficult to write down, but the process is still normal. The temper stable, it also has this representation, so you actually can use it in the same way. And one of the distributions I haven't spoke about so far, but we also have it in the system, and people are using it for financial time series, the student T distribution. It also has a subordination representation, and I actually it's quite natural. You just take the normal with certain parameter, and this would be 1 over v would be I square with a given set of degrees of freedom. And this basically defines a T distribution. It's very easy to write down, very easy to work with in this sense. It's, statistical textbooks. So you can use this for simulation. You can use this for explaining to people. You can use it for modeling, of course. And you model it, and you actually get quite an interesting results and quite valid results out of this. Now, you can take it a step further in a sense. The changes to the market timing, the subordinated, they are independent from day to day. So if today is a slow news day, this does not say that tomorrow will be slow or fast. You just don't know. They're independent events. But you can actually build the model where these events are not independent, and tomorrow's quickness of news will depend on whether or not today was quick or slow. And what you get is so-called time varying volatility. And basically the process is called GARCH, generalized autoregressive conditional heteroscedasticity. I believe it was thing, but don't quote me on that. So today's variance, because as you see here, basically the process that governs how the news come with what speed, it goes into the variance. It goes here. So you have somewhat of a random variance here. And when you model this in a time period, you get time varying volatility. Each observation's variance, not so much the observation, but rather its variance, is represented with a model. So you have a model for, this would be some model F of something, some variables, and somewhere around here we'll have a variance, and the variance will have a model for itself. And usually we have time varying here, and this would probably depend on the previous variance, and so on and so forth. So we're moving up a step in this sense. It's a more complex method. But there is certainly time varying volatility in the financial market. That there are numerous papers to show that. So you have to take this into account into modeling. And this brings us a little bit to the idea of accounting for the speed of the hand for dice roll and the surface roll. You actually take out some of these models when you discuss the stochastic process. So this is kind of fixed. This model here, the parameters, you take them out, and what is left is the random and stochastic component. Okay, how am I doing with the time?
About 20 minutes.
Okay, okay. So let me just get this out of the way. So far, we kind of discussed univariate models, and the problem with univariate models, not so much of a problem, but rather it's not really applicable, because in a portfolio you will have multiple variables, and what you will be interested in is how the variables are connected to one another. And that's why we need to go to multivariate distributions. And the way to describe multivariate distributions is through functions of multiple variables. And we're looking at the probability of two events now. We have one event which would be x1 less than equal than x1 small, and large x2. This would be the second event. And just the same way we have the joint cumulative distribution function, the joint probability density function. And what we have here is actually embedded in the whole idea. There are three functions, so to speak. We have the joint, but we also have in here, if we're not looking at this at all, or we assume that small x2 is actually the maximum value for the outcomes of x2, we will have only this one, which would be a function of one variable, and it needs to be the cumulative distribution function of the first. So we have the joint and the two marginal, they're called marginal distributions out of this. And to get the marginals, you basically substitute y with plus infinity, which would be the maximum for continuous variable. This would come up a little bit later on when we discuss different ways to specify multivariate distributions. But here we have the joint CDF, which defines for us both how the two variables are connected, but also how each of the variables behaves. Now, when we have two variables, we'll be most interested in are they dependent or are they independent, basically. So the definition of independence is if we can write the joint probability density function or the joint cumulative distribution function as a product of the marginals. So just to have it here, this would be something like this. So why this kind of implies independence? Well, one of the properties of a cumulative distribution function is that any value of infinity would be equal to 1. So if we take the marginal, doesn't really change at all. So this definition of independence makes sense. So no matter what y does, sorry, y does, x can do whatever it wants. So they're independent. Now, if they are not independent, then they are dependent, of course. How to measure dependence? Well, if you know the CDF and you know it in its entirety, you can calculate all kinds of measures, of course. But again, it's useful to have certain measures just to quantify the dependence in a sense, which would make easier to compare, let's say, different dependencies. And one possible such measure is the covariance between two variables. And it's defined like this, quite easy. It's probably some more useful to look at the correlation of two variables, which basically is this number divided by the variances of x and y. Y is a little bit more meaningful. The correlation is between -1 and 1. And 0 basically means no correlations. Now, very important note here. When the correlation is 0, we speak of uncorrelated or linearly independent variables. Two variables can be dependent and uncorrelated. So it's a weaker thing to say that two variables are uncorrelated than to say that they're independent. For independence, we need to factor the joint distribution into the marginal and see that this is in fact true, and so on and so forth. But yeah, covariances or correlations, this is the way we usually measure as a number the dependence between variables. Now, when you have multiple variables, even if there are two, it kind of works out nicely to have all the correlations or covariances and the variances of the variables put into one single entity, which would be the correlation matrix or the covariance matrix. Now, why is it nice to do it? Well, there are certain properties that this matrix follows, and for one it's symmetric because the correlation between x and y is the same as the correlation between y and x. So it's symmetric, and it's positive semi-definite in the sense that if we take a linear combination of the actual variables, which would be another random variable, so we're multiplying variables by some coefficients, summing everything together, we're actually getting a random variable as well. This random variable cannot have negative variance. This would basically mean the positive semi-definite. But having these two properties actually allows us to use all kinds of theory out of linear algebra that specify that we can find square root of the matrix, we can find other decompositions, eigenvalue decomposition, singular value decomposition. Even we don't really need positive semi-definite for that, but it's a possibility. So these properties allow us to do certain mathematical thingamajigs on the matrix. And of course, this is the same for covariance, for correlation, because correlation between a variable and itself is 1. Of course, it cannot be something else. We actually have the matrix is 1 on the main diagonal and something here. Of course, it would look something like this for a correlation matrix. So this is basically the way the standard way practitioners define correlations. And I've given here an example of multivariate distribution. Of course, it will be the Gaussian, as it's easier to work with. And it starts by defining standard normal multivariate distribution, and standard normal multivariate distribution out of independent variables. And since they are independent, we actually know how their joint CDF function, or sorry, PDF function would look like. It's a product of the individual marginals, and the individual marginals would be something like this, times 1 square root of 2 pi. And you do this for each variable. And then make a product out of each and every one of that. And basically this is what I have here. Just this x prime x, when x is a vector, sorry, x should be something like this. This is the scalar product, which is this. Some mathematical notation. So you have this. You have this multivariate, but formed out of independent identically distribution normal variables. And this would be in a two-dimensional space, for example. Outcomes of this variable would form some cloud which would be spherical around 0, and so on and so forth. When we have these variables, this would be x1, this would be x2. What you do is rotate and scale it basically with a linear transformation. So the matrix A is basically n columns and rows, so it's a square matrix. And when you do this, you basically transform this into something which would look like, say for example, something like this. Again around 0, but now it would look much more like an actual ellipsis, and one of the dimensions would be much larger than the other one. It all depends on the way the matrix A is formed. And then you move it somewhere else. Actually, I've actually moved it already, so the center of the ellipse is somewhere around here, so that mu, which is actually mu1 and mu2, a vector, would be this here, the center of the ellipsis. And you get a normal distribution, and you actually can say what the parameters of the distributions are. The covariance matrix, we can actually calculate it straight away. It's just the product of A times A transposed. The mean vector or the expected return is mu. Okay. Now, this is just a primer on multivariate distribution and so on. So, it's a quite important distribution, of course, the Gaussian, used a lot. And we actually can use it in a subordination, the multivariate one. We already saw how subordination works with univariate, but we can actually do a subordination on the multivariate process. So we will still get this fast and slow times, market timing, on a whole vector of variables. Now, of course, the main components of the multivariate Gaussian distribution is the covariance matrix, which was A times A prime. Now, the covariance matrix, as we saw, it's not really a measure of dependence, it's a measure of linear dependence. And this kind of leads to certain issues with correlations. For one thing, it does not allow for different dependence here in the center and out here in the tails. Because A very usual thing about financial instrument is that you have a more or less independent cloud here somewhere in the center, so which would imply a correlation of 0, but then you get observation here where the market was just crazy and both stocks lost. And this, you can either say the correlation is something like this, which would greatly affect your whole idea of risk management, because you're using these observations to mean something about here in the center, or you can actually handle the question more theoretically and put a different measure and a different way of specifying dependence between the variables. That would actually be something more like tear shape, like something like this. And the way you do it is you use Copulas. Copula is actually quite an advanced statistical entity, but it's a centerpiece of what Cognitive does as a risk management, and it allows things like this here, which you cannot actually measure them with correlation. A correlation is a single number that needs to take into account everything here, so it's going to be much more based around here, and either it's going to get confused with these values here and take them all into account, or just ignore them. So you need this thing here. And the Copula has also another very interesting thing which is quite useful in financial management. We already saw that the multivariate distribution actually contains information for both the co-movements of the variables and the behavior of each individual variable. The Copula actually allows us to separate these two. So we have one function which controls how the variables work together, and we can plug into this function how each individual variable is behaving. And this need not be the same thing. One can be an extreme case, for example. One can be stable, one can be temper stable, and one can be normal. If you have three variables, this would be the behavior of each individual, of each marginal distribution: stable, temper stable, normal. But then their dependence is disconnected from that. We have multivariate stable, we have multivariate temper stable, we have multivariate normal. This is not the multivariate model that we use. No, we use the Copula, and we plug the marginal distributions coming out from the three models, and they are different. And basically it's this point here, and we can have general dependence, and we have dependence of extreme events. I don't have graphs of the Copula. I just wanted you to know the general idea of Copulas and what they offer and why we want to use it. So we get to the last topic we're gonna cover this hour, and basically the idea is, okay, we have our asset and we want to explain its movement with something else. Say, for example, we're looking at the log return of an equity. This equity operates on a market, let's say the S&P 500, it's part of the index. So maybe the movements of the index have some explanatory power for the equity as well. It's quite likely that if the index goes up, the equity will go up as well. But we want to know what's the dependence there? How to quantify that dependence? And it need not to be only the market, the S&P 500. It can be something else. It can be, let's say, extreme cases, the GDP of the country that the company operates in. Maybe that has a bearing on the log return. maybe exchange rate. That's if it's a multinational company. Changes in exchange rate may hurt its earnings, which would then translate in losses on the market. And the way to do it is basically to define a factor model on that. And I have here the general equation of the regression, which is the factor model. And we have y, our dependent variables, alpha, which usually goes for an intercept, is the other way to say about the coefficient. This captures some non-random movements, non-random, actually constant movements in the log returns. And we have then factors, which would be the axis, x1 to xk, and the coefficients of linear dependence, beta from 1 to k. Now, this would basically define non-stochastic equation for the way the equity would move. Now, of course, as I mentioned, we may not know every factor there is. We may not be able to express every factor there is in a certain combination. So that would be one reason why we would add a random component here. And the standard example would have epsilon be a Gaussian variable with 0 expected return and some variance. So this would be a residual or error term or what have you. What we don't know in these equations are basically the betas, and we are mostly interested in the betas. We also don't really know this. Now, we would refer to this as a time series factor model if the actual data for y and x are time series of certain factors. So y can be the low returns of an equity over the past 1 year. And axis would be the index returns over the past year as well. Now, this is the simplest case one can write of a factor model. There are multiple ways that we can actually expand on this. For example, for a purely time series model, one has actually y with an index t, so this is just in a time domain. Let's have only one factor t and epsilon t. One can have normal, where we have different sigmas for every day. This basically changes the model a little, not only a little bit, but significantly. The different ways to estimate these things are needed. One can have different distribution. One can have a t distribution here with location 0, say some scale and new degrees of freedom, or some other methods. I mean, there are multiple of these things. Anything here? Not really. We'll come back to this next hour when we discuss cognitive and how we actually fit the whole idea here. Another factor model, which basically, okay, let's have it here. We're not gonna have t. In this factor model, there's implied information that we are putting in the model, and the implied information is that we actually know what x is. And this may not always be the case. We may not know what are the factors that explain a certain variable. So we assume there are such factors, but we don't know them. And we don't know what their data is, we don't know what they represent. And a way to deal with this is basically to perform, one of the ways to deal with this is to perform a PCA analysis. Now, PCA analysis is basically a rotation, just like here, of the factors. But we are rotating them, we're starting from this basically rotation. We have this data, so we have two variables, normally distributed, and we want to rotate them and find something which would explain the factors. And the way to do it, we basically always assume expected to turn 0, is to find a direction, so another coordinate system which has the highest variance. So in this case, we'll need to find this direction, because if we have this here, this is the highest variance in the variables. So this would be our first principal component. And of course, there are two variables, so we need to find the second direction. And the second direction would be let's find it here. So this is orthogonal in terms of correlation. So the two factors are actually independent. But the first one has the highest variance, the second one has the second highest variance. In this example, only two are needed. Now, if you have more, of course, if you have 20, you need to find 20 such directions. But the interesting thing happens when you take into account the variance explained by this factor. You can say that the variance for the other factor is just the error. It's this random component here which we actually don't want to look at so much. We want to know what's the behavior of this direction, not so much about this. So for these two variables, we'll take only one factor and say, okay, we have one factor here, and use that. And the rest is just residuals. And it turns out that this model is really nice for yield curves. If you remember last time, all the interest rates belonging to, let's say, a single country, Bulgaria, for example, they form a yield curve. And if you perform the PCA on the yield curve, you explain the first three factors explain almost 90% of the variance there. So what you're leaving out is just 10% of the variance. Of course, the problem here is that you don't know how many factors there. Am I done? No. Okay. We can actually do the last two slides the next hour.
Yeah,
Okay, if everything is.
we can continue 2 hours then.
Yeah. Well, thank you. Thank you.
This program is brought to you by AUBGTalks. For more, please visit us at aubg.edu/talks.